How's it going? Okay. Hope everyone's doing alright. Are there any questions before we get started? Next test. What we're going to do is this week we're going to wrap up the material for 7, 8, and 9 that we need to cover. And so Tuesday next week, we'll only meet on Tuesday next week because of the holiday. Tuesday next week we'll review, and then the test would technically be the following Tuesday. But again, I would actually give you a little bit extra time on that test as far as when it's available, because it would basically be available from Tuesday next week until Wednesday the following week. So you'd have basically 8 days over which to complete it, something like that. Yeah. We will have a final review. We'll also have, well, after the test, we'll just have one more class essentially before the final. What I think I'm going to do, it's like on our Thursday, we'll have we'll go over new material for chapter 10, and then on Friday, we'll go over the review. So that'd be like an extra section, and the video will be available. So if you don't want to do that on a Friday, that's fine. I understand. But we'll do it from like 10 to 12 on Friday, which is my office hours. Unless I have a meeting, then I'll just switch it around based on that. So, which I don't know what it's going to be like. So. That's my plan currently, at least. And that should get us through everything that we need, most everything that we need. I will be skipping, I think, 9.3, but overall I think it'll be in our best interest to skip that instead of chapter 10. So. Had to choose one to get rid of. So. Now I say chapter 10 like it's this massive thing. What we cover in chapter 10, basically we can do in an hour and a half. It'll be a little bit of a stretch, but I'll do my best. Okay. Are there other questions? Ideally there would be, but I don't think we have any time to do another part of the project, so I'm not going to force that on y'all. So I think we'll just stick with the 2 parts. I really wish we could have had this class in the classroom and been able to do it that way. I feel like the pace would have been a little bit better, and we actually would have been able to work on the project in groups like I intended. So. And collect our own information, for that matter, not use old information. Okay. All right. Section 8.2 is what we'll cover today, which is on the distribution of the sample proportion. Okay. Here we go. All right. So we're talking about the sample proportion today. Now, this is something we haven't talked about at all. We've talked about mean, we've talked about standard deviation, but we haven't really talked about proportion. A proportion is easy enough to consider that a proportion is a fraction of the population. Like we say, okay, what fraction of the population prefers vanilla to chocolate ice cream, for instance? What fraction of the population walks to school instead of traveling by vehicle? You know, so there's different ways that we can look at that, but it's really just the number of the number of individuals in the population divided by the total population that meet some requirement, whatever it is that requirement is. So, proportion of a population this is represented by the variable p. Okay, and it's not underlined. I just underlined it for whatever reason. And it's the fraction of the population that does or does not have a certain characteristic, I guess we could say. That does or does not have a certain characteristic. Okay. Now we want to look at the sample proportion. The notation we'll use here is p hat thus named because we've taken the letter P and put a hat on it. And p hat is calculated as x divided by n, where n is the sample size, as always, and x is the number meeting a certain that does or does not have a certain characteristic. Okay. So that's our calculation of p hat. So we could say, for example, um, 500 Midlanders are surveyed. About, what can we survey Midlanders about? Pretty much anything, really. will be relevant. Well, not too relevant. 500 Midlanders were surveyed about whether they drive a truck. And that could mean any kind of truck, let's say. And 147, which seems low, responded yes. Find P hat. Okay, so again, our calculation of P hat is just the number that do or do not have a certain characteristic, which is the number that drive a truck, 147, out of the sample size, which in this case is the 500 that we surveyed. And so we take 147, divide by 500, and that gives us 0.29, what is that, 294? Okay. So, roughly 29.4% of the population we would expect at that point. This is not only a sample proportion, but it could also be represented as a prediction about the population proportion. Now, if we know the population proportion, that's something else, that we'll be able to do some different things there. But that'll be something we'll talk about in a moment. There's a few other things we have to discuss first. Okay. For a, well, let me, I don't want to just give this as a list. We have a condition for normality. I should probably introduce that first. And so what this states is that in order for the data to be considered approximately normal, the following must be true. And that is that n times p times 1 minus p must be greater than or equal to 10. Now, so we have a proportion p, this is population proportion, and then we have our sample size n, and so n times p times 1 minus p must be at least 10. Now, if we think about our value for P, our proportion, this is going to be a number between 0 and 1. And so 1 minus P will also be a number between 0 and 1. So their product, the product of two numbers smaller than 1 is smaller than 1. It actually gets smaller in the process. Like if two decimal value numbers are multiplied together, we get a smaller decimal value as a result. Like 0.5 times 0.5 is 0.25. Okay? And so what we're saying is that, okay, we got these two numbers less than 1 right here that multiplied together. We multiply that by our sample size n. N has to be big enough that we get a value bigger than or equal to 10. Okay? I think we have a second requirement that n must be less than 5% of the total population as well. I'm not seeing it in this textbook, but I know that's one that we've used. Well, oh, there it is. I see it. Yeah, they stated it, but they didn't put it as part of like a formula or anything. It's just in the middle of the text. Anyway, so we must meet this requirement that, and generally that means that n itself is going to have to be at least 100. Could be a little bit smaller, but maybe 30 or 40 will do in some cases, depending on the value of P. But more than likely, it will be closer to 100 or more, which is reasonable because we like to have a decent sized sample at least that we can pull from if we're talking about a large population. Now, on the other end of things, we don't want our sample to be too large because also, which I just wrote from we have the requirement that the sample size n lowercase n is no larger than 5% of the population size, capital N. We can summarize that by the statement n, little n, is less than or equal to 0.05 capital N. Okay? What this guarantees us to an extent is that our sampled values are independent of each other. Basically saying that as long as our sample is less than 5% of our population, we can be reasonably certain that individuals we select for our sample, if we create a second sample, it's unlikely that we'll select the same individual twice, and we'll have unique samples, basically. And so, that way, one outcome cannot affect the success or failure of any other outcome. So yeah, whenever whether we're working with populations of people or anything else, we have to consider that. For a city like Midland, where our population is, what is our population nowadays? Is 140? 140,000, 120,000, somewhere in that range. Let's say 130,000. I'll split the difference. So assume for Midland, N is equal to 130,000 people. What is the largest sample we could possibly take to meet this condition? Okay, and so we just say 0.05 times n will be 0.05 times 130,000. And see, that works out to be 6,500. So as long as our sample does not exceed 6,500 people, if our population is 130,000, then we'll be okay. And more than likely our samples will be more like in the sub 1,000 range, just for convenience sake, if more than nothing else, more than anything else. Convenience on our part, like not really convenience sampling, but as researchers, we, it's difficult to acquire data sometimes, and especially if we're doing due diligence and we're being responsible about our methods of selecting individuals, not just doing convenience sampling, but trying to stratify our samples and collect data from different subgroups in a relatively equal manner. Or even a cluster sample or a combination sample like that. It's unlikely we'll get higher than 1,000 or so, just because of the sheer amount of effort it takes to do that properly. Anyway, so, and it turns out 1,000 would be good enough, because it will easily meet our previous requirement, if n is 1,000. But also meet this later requirement that it be less than 6,500. Okay. So we have those two requirements. Now we talked about the one thing we haven't talked about is the standard deviation of proportion. That's the other thing I need to discuss before we actually look at the z-score formula. And then we can work some problems. So, standard deviation. And let's say this is standard deviation of the sampling distribution p hat. Well, it won't be p hat. Standard deviation of the sampling distribution, let's just leave it at that. We'll call it sigma sub p is equal to the square root of p times 1 minus p over n. Yep. So that's how we'll have to calculate our standard deviation. It's relatively simple as far as standard deviation calculations go. It's sort of like the standard deviation for binomial distribution, but we've put the numbers in different places than we did there. So it's about on par with that as far as level of difficulty in calculating it. anyway, we expect this to be a relatively small number because p and p is going to be a number less than 1. 1 minus p will be a number less than 1, and n will be at least 35 or so. And so this, even after we take the square root, which would actually, the square root of a decimal makes it larger, a larger decimal. So the square root of 0.04 is 0.2, which mirrors what we said previously about multiplying decimals. It's not important if you're not sure what I just claimed there. But what ultimately happens is that we get a relatively small number. I mean, it'll be a decimal because our proportion is already a decimal. Okay, everything here we're working with is going to be a decimal, essentially. And we'll have to combine them together and then calculate from there. Okay, so normally what we have to do in a problem is we'll check this condition, that n is less than or equal to 0.05 n. We'll calculate the standard deviation here, and then we can look at the z-score and then find our lower and upper bound and calculate the probability of something occurring based on that. We're finally at a point where we can answer a question. So our z-score for a proportion, or for a sample proportion, I should specify, z is equal to p hat minus p divided by sigma p. It's pretty similar to our original z-score calculation, x minus mu over sigma. The population proportion kind of plays the role of mu in the world of proportions. We have our standard deviation down here, and then we have our data value. Actually, it's probably closer to 8.1, actually, when it comes down to it, because it's a sampling distribution also. But for a proportion here, 8.2 rather than a mean in 8.1. Anyway, and then once we calculate our z-score, then we basically know what to do from there. It's still a normal CDF operation on the calculator. We'll draw our normal curve and then get a lower and upper bound and then put it into the calculator. Alright. I would like to look at let's see, let's start with number 18 on page 413. According to creditcard.com, 29% of adults do not own a credit card. So in part A, suppose a random sample of 500 adults is asked, do you own a credit card? Describe the sampling distribution of p hat, the proportion of adults who do not own a credit card. Kind of an interesting question. Basically, I'm sorry. They didn't give us, you'll notice they didn't give us how many adults have responded yes. What they want us to do here is check those first two conditions, which is to check that n times p times 1 minus p is greater than or equal to 10. And that n is less than or equal to 0.05 capital N. Okay, so this takes care of our what we call our preliminary requirements. On the test, I'll be a little bit more straightforward in asking this than the way the book does. Anyway, so this is P right here. This is the population value that, or proportion for the population that we're using. So we'll use P equals 0.29. Remember, whenever we use that in a formula, we'll have to change it from a percent to a decimal. So n times P times 1 minus P will be 500 times 0.29 times 1 minus 0.29. So it'll be 500 times 0.29 times 0.71. Well, I'll go ahead and multiply those together. Times 0.29 times 0.71. And I get a value of 102.95. And that is definitely bigger than 10. Sorry about that. It's supposed to be 10, not 0. Now, as far as capital N, they told us 29% of adults do not own a credit card, according to a website. We could assume that this is just the United States rather than an international survey, which is probably a valid assumption. But even if we're just looking at the United States, it's 300 million people. How many of those are adults? Probably in the realm of 225 million adults. 3/4 of the population. Maybe higher, actually. But we can safely assume at least 225 million adults in the U.S. 3/4 of the population of the U.S. or higher, or adults. If we define that as being age 18 or older. I think that's a reasonable assumption. So we'll let N be 225 million. So it's 500. So what is 0.05 times that? .05 times 225 with 6 zeros on it. So 5% would be 11,250,000. So as long as our sample didn't exceed this number, we're okay. So I feel like we're pretty safe. We only surveyed 500 people, so we don't need to get too excited about this result. Okay. So, again, in the book it said, describe the sampling distribution of p hat. Really what they're asking us is to check these conditions for normality, as we call them, and that we're not exceeding a certain size. Part B, what is the probability that a random sample of 500 adults more than 30% do not own a credit card. So for n equals 500, probability that more than 30% do not own a credit card. Okay. Now, so we know P is 0.29, little p. N is 500. This is P hat right here. P hat will be 0.30. Because we want the probability that more than 30% of that sample of 500 people, so our sample proportion, what's the probability it's higher than 30%? So we'll use P hat equals 30%, and we'll find the probability that we can end up with a number that size or larger based on this. We still have to find sigma P, which I'm kind of at the bottom of my space here. I'm going to go to the next page to do that. So let's see, we said n is 500 and p is 0.29, and we want p hat equals 0.30 or larger. Okay. So we need to calculate sigma p. It's p times 1 minus p over n under the square root. So that is 0.29 times 1 minus 0.29 over 500. So 0.29 times 0.71 over 500. Let's see. So what I'll do on the calculator for this is do square root, and then we can do 0.29 times 0.71, and then divided by 500. We can just do it all in one step, close parentheses. And we get 0.02029. So I would go to 4 decimal places here, just because we're already working with decimal values as part of this formula, so we don't want to lose a whole lot of accuracy. I would say let's go 0.0203 for this sigma. So it may be a little bit further than we need to go, but I think it'll give us a bit more accuracy. Okay, 0.0203. Now we can calculate z. Z is equal to p hat minus p over sigma p. So it'll be 0.30 minus 0.29 divided by 0.0203. So we'll take 0.01 divided by 0.0203. We get 0.49 as our z-score. Again, on our z-score, we only go to 2 decimal places. Because we know we're rounding here, we don't want to over-round here and get a different result. If I had truncated this to 0.02 and left off the 0.3, this would have been 0.50, and it would give us a little bit different result. So we have a z-score of 0.49. We know z is 0 in the middle, so 0.49 is a little bit to the right of that. And we shade it to the right because we said we want p hat to be 0.30 or larger. That means everything to the right. It said more than 30% in the description, so that's where we're pulling that from. So we look at this shaded region now, and we have a lower bound of 0.49 and an upper bound of 10. And from here we just go into our normal CDF operation, like always on the calculator. Second, data, distribution, normal CDF, 0, wait, 0, 1, there we go, 0.49, and then 10, and then calculate. And we get 0.3121 after we round. Okay, the book agrees. Let me get that out of the way. So that's our probability that if we took a sample of 500 people, knowing that the population proportion of people that do not own a credit card is 29%, we're saying there's a better than 31% chance that we can survey these 500 people and have 30% or more that do not own a credit card. It seems kind of convoluted when I say it like that. I don't mean to make it difficult. What we're actually testing here, which is a good thing to address, it's a lot like what we're doing in the last section. Like, we know this common data value exists for the population, but in a sample we know things can be a little bit different. And so the idea is that we can get different calculations for a sample, but we also know that they shouldn't be too different from what's going on with the population as a whole, especially if we have a decently large sample size. And in this case we have 500 people, so we know that's a pretty decent sample size, so we expect it to be more or less in line with what the population proportion says here. And the population proportion says 29% of the population doesn't own a credit card. Now, 30% is actually not that far from 29%. That's why we have a pretty decent chance of getting a little bit of variation from our population proportion to what we calculate from the sample. So it may be that we get a few more people than normal in our sample that do not own a credit card, and that's reasonable. Okay, this looks perfectly reasonable because our probability is higher than 30%. Okay, that's well within the realm of possibility. Now, if we had said instead of 0.30, we had said 0.35, then we'd really be starting to reach, especially with our standard deviation being only 2%. Which might be the next question. No, it's pretty reasonable. Oh, gotcha. Yeah, let's work the other parts, and I think maybe this will explain it a little bit better. Okay, part C. Okay. In part C, what is the probability for a random sample of 500 adults between 25% and 30% do not own a credit card? Okay. Now, whenever it says between, that means we have two, in this case, two sample proportions, so we need to calculate a z-score for both numbers. Now, the good news here is we can use the same sigma, our same standard deviation we calculated in the last part of the problem. In fact, we can even move that calculation to part A, where we, which I may do in the test. It's just on part A, have you check both conditions and then calculate the standard deviation, and then we can do our calculations based on that. So I'll have to look at that. Anyway, but I'm also not going to ask you like 5 different questions on the test about the same thing, like we're seeing here. Anyway, it'll just be one problem on the test, so I just may prompt you for each part separately, and then it'll count it as part of the total. So. Okay. So we know sigma p is still 0.0203, and we still know that p is equal to 0.29. And so we have p hat 1 equals 25%, or 0.25, and we can call this p hat 2 equals 0.30. But we need to calculate a z-score for both of those numbers. So z1 will be p hat 1 minus p over sigma p. So it'll be 0.25 minus 0.29 divided by 0.0203. So negative 0.04 over 0.0203. For that, we get negative 1.97. Okay. Whoops. Good. We'll also calculate z2, which would be p hat 2 minus p over sigma p. So that'll be 0.30 minus 0.29 over 0.0203. So 0.01 over 0.0203, which conveniently we already calculated right here. It's 0.49. Okay. So we have this information. Let me just move that up there. all we really need are the z-scores at this point. So we'll go ahead and make our normal distribution. Negative 1.97 will be further over to the left, and then 0.49 a little bit closer on the right. And we want the area in between. And we can see that's the lower edge, or the lower boundary, and then the upper boundary, that's just our two z-scores. So our lower is negative 1.97, our upper is 0.49. And then we'll just take that data and calculate our normal CDF value. So negative 1.97. 0.49. So we get 0.6635. So our probability that between, like if we take a survey of 500 people, and between 25 and 30% don't own a credit card, that probability is pretty good. Almost 2/3 of the population, almost 2/3 of our sample should fall in that range. Well, sorry. 2/3 of the time we take this sample, it should fall between 25 and 30% that do not own a credit card. Okay. It's important to properly interpret these numbers. So this is the likelihood, what we just calculated here is the likelihood that for a sample of size 500 that we would end up with a sample proportion of between 25 and 30%. So there's a 66.35% chance that our sample of 500 people will give us a result between 25 and 30% that do not own a credit card in this case. Okay, part D in this problem. Would it be unusual for a random sample, of 500 adults to result in 125 or fewer that do not own a credit card? Okay. Now, there is a fundamental difference here that we have in the way that this question is asked, and that is, it says, would it be unusual with a sample size of 500 people, n equals 500, that 125 or fewer do not own a credit card? Well, p hat, we would have to calculate ourselves first. Remember, that's x over n, which is 125 or fewer over 500, and I believe that's 0.25. Yeah, that's 1/5. That's a quarter of 500, I believe. I'm going to double check. Yes. Okay. So we first have to calculate p hat in this problem because rather than giving us the p hat value, they gave us the raw data value, and we had to calculate it ourselves based on that formula. So that's something different that I thought it was worthwhile to look at. Now, that's our p hat. We still use p equals 0.29, and we still have sigma equals 0.0203. And so that's still, we're still using the same values there. So now we can calculate our z-score. Sigma p, that's what it is. So 0.25 minus 0.29 over 0.0203. And we already calculated this once. It comes out to be negative 1.97. That's exactly what we did for the first half of part C. Anyway, now we said 125 or fewer, so it's going to be, here's Z, and then we shade everything to the left of that. So negative 1.97, shade to the left. So our lower would actually be negative 10 in this case. And the upper, negative 1.97. So negative 10 to negative 1.97. And we calculate 0.0244. Okay. And so the question is, would it be unusual? Do you remember what we said would be considered unusual from a statistical perspective? What unusual is determined by? Or what the cutoff for being called quote-unquote unusual is? Now I'm not gonna ask you unusual on a test. I'm just gonna have you find the value, and that tells us everything that we need to know. But it does turn out to be that unusual is less than 5%. So we can conclude that yes, this would be an unusual result if we had 125 or fewer from that group of 500 that did not own a credit card. Especially in Midland. There's a lot of people run around here with credit cards that may not be entirely responsible with them. So, anyway. Right. Any questions on this? Okay, let's look at number 20. And then I think that's all we'll have time for today. But I think that's a nice way to wrap this up. The Pew Research Center recently reported that 18% of women aged 40 to 44 years have never given birth. Suppose a random sample of 250 adult women at 40 to 44 years of age results in 52 indicating that they have never given birth. So before we dive into the actual question here, let's write down what these values they've given us so far are. According to the Research Center, 18% of women aged 40 to 44 have never given birth. So that establishes a population proportion. This is what is known about the population at a national research level. Okay. Suppose a random sample of 250, so we know n is 250 right off. Adult women, 40 to 44, results in 52, indicating they have never given birth. Now, we haven't really used this a whole lot, but that'll be X. That's the number from a sample that meet the given condition. Okay, which in this case is the 52 of that 250 that have never given birth. Explain why this is not necessarily evidence that the proportion of women 40 to 44 years of age and have not given birth has increased since the time of the Pew study. Now, before we dive into the calculation of the z-score and everything, we need to do our preliminary work, and this will kind of simulate what we'll need to do on the test. So I may give you the data in this form, but first we need to show n times p times 1 minus p is greater than or equal to 10. So that's 250 times 0.18, and then 1 minus 0.18 is 0.82. Now we just multiply those together. We get a value of 36.9. And 36.9 is definitely bigger than 10, so we're good there. Second, we want to show that n is less than or equal to 0.05 times n. This one's a little bit more challenging because it requires us to know the number. Capital N is basically the number of women age 40 to 44 in the United States. And this is a very specific age range, and I don't know that we could necessarily approximate it, but before we said we figured, roughly 3/4 of the population are adults at least. And we're just playing it safe there because it's probably a little bit more, but well, maybe not. I felt like it was pretty reasonable. Anyway, so let's say 225 million adults in the U.S. Let's go further and say half of those are women, give or take. It's a relatively safe assumption. Well, yeah. Anyway, there's other concerns there, but from our approach doesn't change it drastically. So we could say just conservatively 110 million women. Probably it's probably more than that. But anyway, but how many of those women are in the range of 40 to 44? Let's see. Average life expectancy is what, 80 nowadays. Especially for women, it's a little bit higher life expectancy than men. And we're looking at a 5-year age range out of 60 plus year total. So maybe take 1/12 of that. So we're looking at 10 million women in this age range. This is needlessly complex, I think. But I would estimate 10 million here for N. And I probably overthought that one a bit. I mean, even if we just said it was 1 million, we're going to be pretty safe in this case. Because N is only 250. And then 5% of 10 million is 500,000. So I feel like we're okay. We had a lot of play there, I guess you could call it. So there wasn't really a need to. We could have just lowballed the number and been perfectly fine. We could have said there's at least 1 million women in this age range, and we're good. Anyway, so more, we've reasonably demonstrated that this to be true. Okay, check mark there. So now we need to calculate sigma p, which is square root of square root of p times 1 minus p over n equals square root of 0.18 times 0.82 over 250. So square root 0.18 times 0.82 divided by 250. Whoops, did it twice, but that's okay. 0.0243, rounding to 4 decimal places again. Okay, and finally, we need to calculate p hat. $52 divided by 50, 250, sorry. It's going to be 0.208. We'll call it 0.21 just so it's the same number of decimals as p. We could do 2.208. That's probably not the end of the world. Yeah, we go ahead and do that. We'll round after we find z, not before. This is an exact value. It's one more decimal place. It's not a huge concern here. Okay. So now we can calculate z, our z-score, which is p hat minus p over sigma p. So 0.208 minus 0.18 over 0.0243. So what is that? It's 180. So it's 0.028 over 0.0243. It's not too big. 1.15. Okay. So, let's go back to the question because we have to figure out which side we have to shade to. Explain why this is not necessarily evidence that this proportion of women 40 to 44 years old that giving birth has increased. Increased is their key word. So we want the probability of getting this value of z or more. So we draw our normal curve. 1.15 is to the right of 0. And increase means we want that number or higher. Our lower bound is 1.15. Uh-oh, pen's going out. This is a minor crisis. Anyway, I don't know where my other pens are. Shoot. Let's see. So I can tell just from looking at this. I'll have to write it down, I think, for everyone. Our lower is 1.15. So I'll enter that in. Put it where you can see it. And our upper, we'll say, goes to 10 on the right. Calculate that. So we get a value of 0.1251. Now, so that means the likelihood of this outcome, or higher, is within the realm of possibility. 12.5% of the time we should expect to get from a sample of 250 at least 52 or more that would have never had children. And so unless this is like a really small number here, like we get less than 0.05 maybe, where it is technically considered unusual, unless that happened, I think we're okay saying that it hasn't actually increased the we can't really claim that the probability or the ratio, or sorry, the proportion is what we're looking at. Can't really say the proportion has increased from what is established by the research center here. So this is still within the realm of possibility that we would get this outcome. So it's not really earth-shaking. If we'd come up with it almost have to be 60 or 70 out of 250 for that to be really unusual, I think. Well, the p hat would have to be bigger than like we have what was our standard deviation? 2.5% basically. So 3 of those. Yeah, so we'd have to get about 25%, which for n equals 25 would be in the neighborhood of 63 people out of 250. Yeah, for this to really be considered unusual. And if that happened, we might want to rethink our claims. Now, what the other process we would actually use here is called hypothesis testing. So that's something we'll look at in Chapter 10. That's more what this question implies than what we're talking about right now. So we'll come back to this kind of thing later. Is what it ultimately amounts to. For homework or just to practice, I would recommend practicing, let's see, I'll try 17 and 19 just for homework, and then we will continue from there on Wednesday or Thursday. Sorry. You all take care and have a good day. Bye.